I want to do two examples of these infinite geometric series where we are calculating the infinite sum. We're calculating the sum that this gets closer and closer and closer and closer to as you add more and more and more terms. So we have in this one 2 plus 2/3 plus 2/9 plus 2/27. I hope we can all identify that the common ratio here is 1/3. And of course, a1 is just 2. And so we want to use this formula for a geometric series. And we're first going to recognize, all right, this is in fact 1/3 is in between -1 and 1. So we're good. We can actually do this. And we're going to just use the fact that this infinite series, this is the rule we derived in the last video, is equal to 2 divided by 1 minus the common ratio, 1/3. So this is just 2 divided by 2/3, keep change flip, 2 multiplied by 3/2, otherwise just known as 3. So I think that's surprising, probably. You look at this sum, 2 plus 2/3 plus 2/9 plus 2/27, and you keep doing it. The next one would be 2/81, and then 2/243. And you keep adding those, and it feels like, wow, we're just going to end at 3. And I encourage you to type in as many terms as you want into Desmos or into your graphing calculator, into whatever, and you're never going to quite reach 3. And so maybe that's frustrating too. You're like, wait, I never actually get to 3. And that's true, because of course you can never actually type in an infinite number of terms. But as we go to infinity, as we add as many terms as we want, this gets as close as you want to 3 as the period, as close as you want to get to 3, right? You can, if you want to get within 0.0001 of 3, there's enough terms that you can add there. And if you want to get even closer, you add more and more terms. And so we do say that it's equal, though it might require thinking of equals slightly different than slightly differently than how you had thought of it before. But we do say that this is equal to 3. So I'm going to write that in. This is equal to 3. There we go. Now let's do another one, but it's going to be the same kind of thing. Here we have 1 minus 0.1 plus 0.01 minus 0.001 plus 0.0001 minus 0.00001, and so on. Either way, it's not as bad as it looks. We have the first term, a1, is equal to 1, and the common ratio here is really important. It's negative 0.1. It's negative 1/10. So whether you want to write this as 0.1 or 1/10, I'm actually going to go back and change my opinion. It's negative 1/10. I'm sticking with my fractions when possible situation, because otherwise you're going to get some infinite decimal, but that's really hard to do in this situation. Okay, so we're just going to use our formula that we derived before. S is going to be equal to A1, which is just 1 in this case, over 1 minus R, which is negative 1/10 in this case. This is equal to 1 divided by, 1 minus 1/10 is 1 plus 1/10, which is 1 1/10, or 11/10. And 1 divided by 11/10 is 10/11. And that's what we get. Now, if you wanted to write this, I think it's going to be 0.909090909 or 0.91. I don't know. I actually always forget what it is. I think it's 0.90909. I should just do it. 10 divided by 11. Yeah, it's 0.909090909. On and on and on forever. I'd much rather see 10/11s because that's much easier to deal with. And so there we go. That's our answer. Not too much more to it. It is, it is a formula at the end of the day, and it's a really handy one, and one that's going to show up in all different fields of math. Okay.